Hello, IoT students. This is Dr. Kelley, and I am uh, traveling today, and so I've asked Taylor to present this recorded lecture for you. Um, Last time we were talking about networks, but before we uh, continue with that, um, I have a first assignment for you. So the first assignment is for you to either borrow or purchase a Raspberry Pi 3 or 4 starter kit, and you can find them at any electronic store or online store. I'm not necessarily endorsing Amazon, but you can find them there quite easily. And um, uh, if you would like to pursue an IoT project that does not involve Raspberry Pi, and I've had a number of students in the past who've done that, so that is okay. Just let me know what you're planning to purchase in place of that. Also, if you could read chapter 1 of Baga Mezzetti, 22 through 46, while also maybe starting your familiarity with Python if you're not familiar with it. There are a number of tutorials that you can pursue for that. One of them is the Code Academy Python tutorial. There's also so that for that you have to create a Code Academy account. So just follow the link that's shown. Also, if you could download PyCharm, if you're using Anaconda, PyCharm does integrate with Anaconda, so that's fine as well. So please go ahead and download PyCharm and integrate it with Anaconda as appropriate. And so you can find that online as well. And for that, use your UTSA email address, and you should be able to get a free download for that. Okay, so that is your first assignment. In terms of where we were last time, we were basically talking about the internet, and keeping in mind that you know there are a lot of nuts and bolts perspectives on the internet. One of the key things is you have hosts, which are basically your end system or your endpoint systems. They're running network applications, so applications that need to communicate with other uh, applications over a network. And that network consists of communication links which have certain bandwidths. The information exchanged between the applications over the network is subdivided. The message is subdivided into small packetized units and communicates over routers and switches. Um, so if we look at the uh, network itself, so let's just take some notes. Then we can see that the network itself um, sorry, give me 1 second. So the network itself, so basically we can say that the internet consists of a network of networks, consists of a network of networks. Consists of a network of networks. It also, get this out of your way. Those networks use protocols. and there are a number of internet standards. Okay, so this is basically, and the internet standards groups are there's a RFC and IETF are basically the internet standards groups that are typically used. Okay, so all right, so if we go back to here, okay, so let's go forward. Okay, so as an example, you know, on the internet, we can request a file. So, for instance, one of the things you do is you make what's called a TCP request connection, and TCP is the transmission communication protocol, and we can get a TCP response and receive a particular file. So that's an example of the use of TCP. So TCP in this case would be a protocol that you're using to communicate between computers on the internet to receive certain information. Now, the TCP stack itself, let me broaden this out here. The TCP stack itself is a 5-layer stack, and consists of the following layers. So let's just make a note of that. So if we look at the internet as a layer of protocols. Okay, then there's a 5-layer TCP IP protocol model. The first layer is known as the application layer. So let's just go ahead and number these here. Okay, so the first layer is the application layer. So it supports network applications. So the application you're running at the highest layer. The next one is the transport layer. And the transport layer is basically right under the application layer, and it uses certain protocols in order to communicate information across networks to specific applications. Below that is the network layer. The network layer basically consists of what are called routing datagrams or IP datagrams that you use to communicate information from one network point to a second network point. Below that is the link layer, which refers to the data transfer between sort of neighboring elements in the network. And then finally is the physical layer. And these are actually the bits on, you could say, on the wire or over the air, okay, or on a medium, okay. So you're communicating over some medium, which could be wireless, it could be wired, it could be optical, okay. So that's the physical medium. And over the physical layer, this is normally signal, waveform signals, okay? Whereas everything else involves binary information transference, okay? All right, so these are the 5 layers of the TCP/IP protocol. Last time we mentioned that in order to communicate, so if we take this 5-layer network model, okay, so this is the 5-layer network model, okay, and sometimes you'll see the words OSI associated with that, or Open System Interconnect Model. So what happens with the 5-layer model is when you're at a specific layer in the protocol, those layers communicate with each other as specific services or functions. And so if I'm writing an application, I only want to think about what my application needs to do to interact with the application on the other side of the network. Okay, so that's the only thing I want to concern myself with. I don't want to really be concerned with, what kind of network routing protocol am I using, all right? At least to the extent of, do I need to, can they be independently created or do they need to be dependently created? So in some sense, the application can be independently created irrespective of the network IP protocol. However, the application performance and quality of service will depend on the transport layer, network layer, link layer, physical layer considerations. Okay, so we try to isolate each layer so that when we're operating in a particular layer, we're not having to worry about what's happening in other layers in the network. The lowest 2 layers, the link and physical layer, are frames rather than packets, and they tend to their goal is to remove the impacts of any noise or channel operators, such as fading, that have occurred on the medium for transmission. Okay, so one of the things I want to mention is, what are the different components of a network? So let's look at this. Okay, so if we look at a network, generally speaking, we can consider it to be decomposed into sort of the end point devices, and these could be mobiles. Sometimes they're referred to as, you'll see the word UE, user equipment. These could be, a laptop. They could be an IoT device, such as a Raspberry Pi. Okay, and then so you have your sort of end devices as one key element in what's occurring. You then have sort of the connection, wireless access network. Okay, so you have the connection of or let's call it of the IoT device with the network. Okay, so that's sort of the wireless access network. Now, for the wireless access network, let's abbreviate this here. So if we look at that, then normally it's the wireless transceiver on the IoT device communicates with wireless transceiver on the access point, or AP. Okay. So to connect, the connection point to most networks is the access point, or we could have a wired connection between the IoT device and the AP. Okay, so you can have either a wired or wireless connection between your IoT device to the network. So that connection to the network is usually referred to as the access point of the network. The AP, the access point, sometimes abbreviated AP, serves as the central connection from these devices into the network, and the AP basically connects to the core network of the um, you know, of the service provider. Okay. So this is the way you can think about networks. So you've got these end devices, you have wireless access or potentially physical access into the network. And then once you access into the network, you're then capable of connecting to what's called the core network, which is normally not technically the internet, but your service provider entity, and their network is what you connect to, and then they will give you access to the internet. So this is normally what happens. And that's what's shown here. So if you look here, then these would be the end devices, the connection from these devices to this antenna system. This would be considered an access point. Then gives you sort of connectivity into the network. And again, that does not have to be wireless. That can be wired. So connectivity into the network, that then is an access point device. You then go through a router into the core network, or the network core of your service provider. So this is sort of how things work. Now, so you have end systems, you have the internet service providers network that you are then interconnected with. And so you then have not just your network connected to the internet service provider, but everyone else's network connected to the internet service provider. And so we get this concept of a network of networks that we're communicating to for this system. Okay. So the internet has a rich history, and there are many good books that you can read on that. One of the key things to note is the growth. And so in 2016, there are 5 billion devices connected to the internet. And this has led to aggressive deployment of services, kind of a ubiquity of wireless access connectivity. One of the things that I study in my research lab is 5G and 5G new radio protocols. And if you note, one of the things that really spurs is easier and easier and higher performance connectivity into the network itself. So when we connect over 5G, it's almost as if we're taking the internet with us, right, in our devices. So you can almost now think of 5G as sort of part of the emergence of the mobile internet. Okay, so the internet is basically a network of networks. Okay, and it now we don't want to create one network, one tremendously large integrated network. We need to break it up in order for it to be scalable. And so that's what we do. So we break it up into various provider networks. Those networks are connected to access networks that we may gain access to. And then there are what are referred to as internet exchange points that connect various provider networks. There's been increasing sort of emergence of sort of content with service provider networks. So Google's a perfect example of that, where you have applications that Google creates that are basically content, and then they also support and deploy portions of internet infrastructure that those applications run over. Okay, so that's the whole notion of a content provider network. Um, so you can think of the internet again as a network of networks. We have to access the internet through internet service providers. Now, we could all be internet service providers. However, uh, because those providers need to have specifically authorized access, then it helps to limit the scope and to purchase services from those providers. There are regional internet service providers, and then there's kind of tier one internet service providers. Uh, so, uh, AT and T, you know, Sprint. These would be tier one commercial internet service providers, and then there are content providers like a Google that will connect their data to the internet, and sometimes doing so they bypass the service provider network. Um, so if we look at you know if we look at this system, and I'm just trying to blow this up. I think I blew out the screen. So let me. Uh, oh, okay. Well, I didn't blow out the screen. Um, so we've got billions of devices. We have communication links. We have packets that are communicated across the internet, and then we have internet standards. Uh, two of the, and I'm gonna. Uh, okay, so two of the internet standards that I want to make you particularly aware of is what's referred to as IPv4. So, two important networking standards are IPv4 and IPv6. IPv6. So these are two very important internet standards, and you can access them. That's really what's cool. So a lot of the things that we're talking about are easily accessible in terms of information. So, for instance, if you're looking for information about what's referred to as mobility support for IPv4, if you look under if you search under RFC 334, you can find that. So, as an example, um, is mobility support for IPv4. So we can actually access that. And so this is what some of those standards look like. And they're actually fairly dry documents, but they discuss the assumptions, applicability, architectural entities, and there's a whole table of contents here that you can use to review the specific standard. So if you, and they talk about, for instance, broadcast datagrams, multicast datagrams, mobile routers, automatic repeat requests, all sorts of things here. So if you're designing networks, then we need to refer to these documents. But sometimes there may need to be clarifications on operations of networks. So you can actually see the components associated with these specific protocols if they are open, described as open standards. Um, Now, one of the challenges when we're communicating across the internet is delays. Okay, so when we connect IoT devices to the internet, uh, one of the significant um, items that will impact our application are the delays associated with sending network packets across the internet. And uh, so, how do we deal with that? Well, one thing we can do is to look at that. So I brought up. So here I'm on a MacBook. So there's different things we can do. Uh, so one thing we can do is we can use what's called a ping. So many of you have probably done that before. So if something's happening, so let's say we ping mediacollege.com. Okay. And it basically will send bytes across the internet and will tell you sort of the round trip time associated with that. Let me break out of that. I can't believe this. Okay, so I was able to. I was trying to quit that here. There. Okay. And ping is what we use. Also, there's another protocol referred to as trace route. So let's say we're rather than ping, if we try, and I think it's trace RT on the PC. So if we go back and we go to trace route mediacollege.com. Oops, I forgot my E. Okay. So what traceroute will do is it'll show us the information about round trip delays between various points in the network. So let this thing run. Okay, and while it's running, let me state that. So what traceroute does is it'll show you the IP addresses for communication over the network to the destination, which in this case is mediacollege.com. And you can see, for instance, some initial network delays. Now, this would refer to delay of my own sort of local network, and then you can see my service provider and network here. Now, these three numbers would illustrate delays for different trials. So let's say there are three different attempts, and you can see the variation of delays. Ideally, they'd be about the same. So you can see there's some variation here, 26 to 41 milliseconds. And these are round trip delays between different points in the network between my computer here and the server at mediacollege.com. So if you're having issues with delays in your network, you can run traceroute. In the class notes, um, and let me just mention this is 32 bits, 128 bits. So you can run a traceroute, and I've left some links that you can use to review traceroute. So this is something that may come in handy if you find that your algorithms are taking too long. Your IoT algorithms are very sensitive to delay. The other thing that you can run to get network information, and where did my screen go? Here it is. The other thing that you can run to get network information is what's known as Wireshark. And I'm listing in the notes also a Wireshark tutorial. So if you look at this, you can find information. So let's look at Wireshark. So let's see. So this is a Mac, so I'm going to go to Launchpad, and we're going to go Wireshark. So I've downloaded Wireshark, and this is Wireshark itself. And what I'll do is I'll click on the Wi-Fi. So you can get increasing amounts of network information on Wireshark and with traceroute. So definitely review those tutorials, and that information can be very helpful. So let me quit Wireshark here. Okay. Okay. So we were looking here. Okay. So this is one of the things that can often impact your applications. So again, look at traceroute, and it'll send 3 probes, and it'll look at the delays as you're transmitting packets across the networks, and it'll show you the delays at different points in the network. The throughput rate is basically in bits per second. You have a notion of throughput in terms of averages and in terms of a specific instance of operation. So these are 2 concepts you have to keep in mind. So if your application is sensitive to a like a minimum throughput, then you would want to make sure that your instantaneous throughputs always are less than that minimum. If your instantaneous throughput's always greater than that minimum, and or if they're based on averages, then you can use that as a result. Okay, so let's move forward. So again, you can run a traceroute also, and these are 3 delay measurements that you can see. So when you have a chance, do definitely run that. This is an example of the use of Wireshark. You can use it to analyze packets. This is the the 5-layer OSI stack, your application, your transport network link and physical layer, and then the Ethernet frames at the physical layer captured by Wireshark, and it can be used to analyze information. So in order to download that, so Wireshark is a free open source packet analyzer. You can use it to analyze networks for troubleshooting, for the analysis of software communication protocols, and for education. Originally named Ethereal, but it was changed to Wireshark in 2006. All right. So the actual five-layer TCP/IP protocol stack, it was initially the protocol stack layer was initially 7 layers. That's more of a kind of academic sort of perspective. The actual perspective of the network layer stack is 5 layers, and one of the key layers is the IPv4, IPv6 layer, which is at the network layer. Now, the way to think about these systems is you've got an application layer at the top, a transport layer, network layer, link layer, physical layer. And then you can think in between layers, you have certain message types or certain um, organized protocol um, uh, streams that you're sending across the network. So, for instance, in between the application and transport layer, we send messages or data streams. Okay, and then the transport layer will format the information that it needs to communicate as transport protocol packets. Now, they're packets, they're just not IP packets, they're protocol packets. And protocol packets simply are packets structured according to the transport layer protocols. We then have network packets, which are IP packets, sometimes referred to as IP datagrams, and the two principal network layer protocols are what's referred to as IPv4, and we've been transitioning to IPv6. And then below that, you have what are referred to as network-specific frames, and these are all openly available structured protocols. So let's look at IPv4. So now we want to look at the protocol associated with communication across a network. So IPv4 and 6 are what are referred to as connectionless packet delivery services. So they essentially, and when we say connectionless, we mean we don't necessarily set up a dedicated communication link between nodes on a network for something like IPv4 and IPv6. Uh, so this is a specific node. Let's say it's a computer on a network. Um, the network itself is defined according to some um, IP address and some um, um, a portion of the network devoted to uh, you know to the network as opposed to host devices on the network, and so that's what is shown here. It's the various nodes on the network and the IP addresses associated with the network devices and the host devices connected to the network, such as the PC. Now, if we look at these addresses, uh, in IPv4, it's a 32-bit address, and so that's what I had listed here. So IPv4 is a 32-bit address. Um, and so 1, 2, 3, 4. So it's got 32 bits or 4 bytes, with each byte being 8 bits. And so if we arrange those bits from left to right, left being most significant, right being least significant, and we read these as what's referred to as unsigned numbers, then you can see then this would be what? 2 cubed. This would be 2 to the first. That's 10. Okay, so you can list this in a you can list this in a description that's maybe more readable as numbers that can go 8 bits. Unsigned can go from 0 up to 255. So as numbers between 0 and 255 separated by decimals, we'll will basically be all the um, you know permutations of 8-bit um, uh, components or octets that are connected together. So you can see the 5 here. So 101, unsigned, that's 5. That's 2 squared to the 0. So each of these is basically 2 to the L, where L has some number between 0 and 7. 37, so this would be, what, 2 to the 5th is 32. 2 to the second is 4, so it's 36. And then 2 to the first, I'm sorry, 2 to the 0 is just 1. So that's how you get to 37. Then 156, which would be 128. And then you've got 2 to the 4th, 2 to the 3rd, 2 to the second, and that gives you 156. So this is how you sometimes see IP addresses described in IPv4. Okay. Now the networks send information to the transport layer, or the transport layer basically communicates information over these networks. And two important transport layer protocols are what's called UDP and IDP. So let's note that. Okay, so transport layer protocols, and remember we use this for delay analysis and Wireshark for network analysis. So transport layer protocols, two of the important transport layer protocols, one is referred to as UDP, and the other one is TCP, the Transmission Control Protocol. Oops. Okay, so now one of the things is we just have to understand that these are just protocols. And so one of the challenges sometimes with teaching this course is to understand that, some of these descriptions are based on engineers having explored something, realized, oh, it misses something, let me add it to it. Okay, so these protocols just have certain characteristics, and those characteristics are born out of practical considerations that were determined to be necessary for proper operation. So if we look at UDP, User Datagram Protocol, this is basically the protocol that sits between the application and the network. So you're getting all these packets over the network, and then there needs to be some kind of transport layer protocol that takes these packets and applies a kind of filtering and procedural performance to them that will guarantee certain characteristics. So UDP is a best effort protocol, but the IP packets are not guaranteed to arrive. Now, why would you ever design a protocol where the packets are not guaranteed to arrive? Well, if the information essentially goes stale after, if it doesn't arrive in time. So, as an example, voice, right? So if I'm speaking in a sentence and I'm speaking, word 1 through 10, let's say word 1 through 10 is broken up by my a voice coder into packetized voice, and the first word, second utterance, has a packet that's, let's say, slow and arriving, then uh, because voice is time sensitive, then perhaps it's okay if it doesn't arrive. Now, what happens if it doesn't arrive? Well, the receive system knows that that's a possibility in certain cases and would try to augment and or mitigate the impact on the audio quality if there are missing packets of voice that are transmitted. So it tries to account for those things. The point is, there's certain applications where if you miss the packet within a time window, that's it. It's no longer usable. So UDP messages contain a destination port and a source port, and the UDP port is an abstraction for the application. Okay. TCP is the transmission control protocol, and TCP is a reliable stream service. So it creates what we call a virtual circuit connection, and it's more complex than UDP. It involves acknowledgments, and TCP connections are identified by endpoints, including a host IP and a port. Now, you hear a lot about these ports. Really, what ports are sort of abstractions for connections to the application. So rather than saying, application 1 needs to connect to application 2 across the network, we'll assign a port to an application, and we'll say, hey, the port needs to communicate, or you're communicating with a specific port that's affiliated with a specific application that you're running. Okay. We're going to pause here.